the new unit that we're going to start today is called uniform circular motion. You can imagine what circular motion means. I've got keys on the end of a lanyard right now. I swing them around in my head, The keys are going in circular motion, right? They're going in a circle. Object moving in a circle, that's circular motion. Uniform circular motion means circular motion or object going in a circle at a constant speed. Now, notice one important word there, that's speed. Not constant velocity, constant speed. What's the difference? Yeah, velocity is a vector. So if we have an object going at constant velocity, not only does it have to be going the same speed, but it has to go in a straight line as well. If we have an object going at constant speed, the direction can change. And clearly, as these keys go around my head right now, the direction is changing, but the speed is not changing. So uniform circular motion, object going in a circle at a constant speed. Now, we're going to define a few terms here in order to take us along this analysis of uniform circular motion. We're going to start off with three of them. First one is frequency. Where have you heard that word before? Frequency, or the word frequently. It's like frequency.
How often?
Yeah, that's exactly what it is. How often something happens. Now, in physics, we don't define it as how often, but it's like that, right? It sounds a little more technical, but it boils down to the same thing. In physics, we define frequency as the rate at which something happens, or we could simply say the number of cycles per unit time. The number of cycles per unit time. We could say, as the keys go around my head, the number of revolutions of the keys per second. Or if we were talking about the RPMs in your engine, you guys, if you drive, you know that there's a tachometer on the dash of your car that measures the RPMs, the revolutions of the engine, cycles of the engine per minute. The number of up and down of the pistons in the engine per minute. Okay, the number of cycles per unit time. Now, the frequency is given by the symbol F, a lowercase f. Be very careful with this. There are two F's that we use in physics now. One is capital F, which is force. One is lowercase f, which is frequency. They are completely different things. So make sure you call force capital F. Make sure you call this one lowercase f so as to not mix them up. Lowercase f is the number of cycles over the time. Now, that equation is not on your data sheet because it's really the definition. But if you remember that definition, it shouldn't be any problem to figure out the frequency from that. Now, if frequency is the number of cycles per unit time, then the period would be the time per cycle. So how long does it take for the keys to go around my head one time? The time for one revolution. How long does it take the piston in your car to go up and down once? The time for one complete cycle of that engine going back and forth. The time per cycle as opposed to the cycles per time. Now the equation for that, or sorry, the variable for that, the symbol for that is a capital T. Up until now we've seen time as a lowercase t, and it still is. But lowercase t represents any amount of time, just general time. Big T specifically means a specific time of time per cycle, time for one cycle. So we're going to write an equation for that time over the number of cycles. Again, that one's not on your data sheet either, but it comes from the definition. So if you remember the definition, you should be good. I'm going to relate these two together now using an equation that is on your data sheet. If frequency is number of cycles per unit time, and the period is time per number of cycles, then we could say that the period is equal to, how do they relate to each other? How do the frequency and the period relate to each other here? Frequency is cycles per time, period is time per cycle. Yeah? Yeah, they're inverses of each other, reciprocals of each other. So we'd say the period is equal to 1 over the frequency. That one is on your data sheet. Now, before we move on, let's talk about a couple units here. What units do you think period would be measured in? Seconds. What units do you think frequency would be measured in? Yep. Yeah, you could do that. That's not the standard unit. Any more than kilometers per hour is a standard unit for speed, but it's a correct unit for speed, as is revolutions per minute a correct unit for frequency. Absolutely. The standard unit would be revolutions per second, or usually we say cycles per second. Revolutions per second is kind of a specific type of cycle per second. Cycles per second, yeah. Now, there's one thing that means the same thing as a cycle per second, another unit that we can abbreviate a cycle per second as. Do you really want to take a stab at what that is? You've all heard it before. You might not think of it in this context, but you've definitely heard it before. Nobody? The variable that, or the unit that means the same thing as a cycle per second. Boy, nobody? This hurts me that nobody can think of this. This is painful. It really hurts me that nobody can think of the answer for this. No. Hertz. Hertz. Good, Benton. 1 cycle per second is the same thing as 1 hertz, which is Hz. Sorry, go ahead. 1 cycle per second is 1 hertz. 20 cycles per second would be 20 hertz. Now, finally, speed. Well, we know what speed is, right? Speed is how quickly something's moving. If we're talking about this object undergoing uniform circular motion, then we're talking about an object that can have its speed expressed by this equation, v is equal to d over t, distance over time. I'm going to ask you to dig back into your math background now for a minute here. The distance around a circle. We're going to tailor this equation to uniform circular motion. This is a general speed equation, but let's tailor it to this special situation of uniform circular motion. What is the distance around a circle once called? Circumference. Good. And what's the equation that describes the circumference of a circle? Not pi r squared. That's the area, yeah. You know what? No, it's 2 pi r, not 2 pi r squared. If you're anything like I was when I was in high school, hey, then you're going to get pi r squared and 2 pi r mixed up all the time. I was terrible at remembering the difference between pi r squared and 2 pi r. Now I'm not, but I was when I was your age. But since then, it occurred to me at one point years ago, a couple decades ago, that there's a nice easy way of remembering the difference between pi r squared and 2 pi r. Does anybody else ever get those mixed up? Clearly one person does, besides me. Yes?
Yeah, but be truthful and honest.
Yeah. No, you know what? I think that's pretty normal. I think it's pretty normal to get those two mixed up. But here's the way that I remember it now, so as to not get it mixed up now. I just remember like pi r squared. R squared would get me meters squared. Well, meters squared is going to be an area, right? Pi r squared, meters squared gives me an area. Whereas 2 pi r gives me meters, and circumference would be measured in meters, not meters squared. Does that make sense? All right, so the distance around a circle once is 2 pi r. But if we're going to use the distance around the circle once, then we have to use the time around the circle once. What is the time around the circle once? The time for one revolution, the time for one cycle. What is it? Yeah, it's the period. So we're going to tailor this equation, v equals d over t, to v is equal to 2 pi r over t, the period. Now, this one does appear in your data sheet again. V is equal to 2 pi r over t, as does v is equal to d over t. You should recognize that 2 pi r over t is a valid equation only for an object moving in uniform circular motion. Units, of course, for speed would be meters per second, right? R is in meters, t is in seconds, speed is meters per second. We're going to give you a couple pretty straightforward examples here. 5.1, this means chapter 5, right? Download chapter 5 from Google Classroom. Print it off, whatever you want, or grab a copy of the textbook if you haven't done that already from the library, whatever you want to do. This one says the hard drive of a computer stores data on a thin magnetic platter that spins at high speed. The platter makes one complete revolution in 0.00833 seconds, which is a pretty reasonable time actually for one revolution of the platter of a hard drive disk. We want to find its frequency in hertz and in RPMs. What do you think RPM stands for? Rotations or revolutions per minute, yeah. Let's figure out what this frequency is here now. What do we have given to us? What is this 0.00833 seconds? Is that the number of revolutions? Is that the time? Is that the period? Is that the frequency? What is that? That's the period. Good, Josh. That's the time for one revolution, one rotation, one revolution. So we're going to call that big T. If I want to find frequency, we're allowed to say frequency is number of cycles per time, but if we have the period already, then why don't we just say F is equal to 1 over T. 1 over 0.00833. Let's pull this up on our calculator. It's a pretty easy calculation to do on our calculator, but I'm going to show you a little shortcut for it. We could say 1 divided by 0.00833 gives us this value, 120. Or we could just say 0.0083, click one button here, x to the minus 1. Do you know what that does? It flips it over. 1 over that number. And we're going to get 120.4. Oh, why is that slightly different? I missed the last 3 there, right? You know that it should come out to be the exact same answer. So we get 120.048. What units are those? What units is that? It's hertz, yeah. It's cycles per second, or it's hertz. Now, we want that rounded to 3 digits, so we're going to make it 120 hertz. Why do you think I wrote down the unrounded number? Because what? Sorry, I didn't hear that.
We have to convert it to RPM.
Yeah, okay, so we have a final answer here, but yet it's not a final answer because we have to use that number in order to convert it to revolutions per minute. Good. Any ideas how to convert it to revolutions per minute? This is revolutions per second. You want revolutions per minute. How many minutes in how many seconds in a minute? 60. So what are we going to do here? Multiply by 60 or divide by 60? We're going to multiply. Yeah, we're going to multiply by 60 because, of course, you're going to get more revolutions in a minute than you are in 1 second. So let's multiply that by 60, and that's going to give us, I believe it works out to be 7.20 times 10 to the 3 RPMs. That's a pretty standard speed for a hard drive platter spinning around 7,200 RPMs. You can buy hard drives to replace the hard drive in your computer that have a higher frequency. What do you think the benefit of that would be? Yeah?
It writes to your disk faster.
Yeah, it's faster access time to your disk, right? You can write to your disk faster and you can read to your disk faster. I mean, imagine if you're trying to, if the reader in your hard disk is trying to read data from various points on the disk and it's spinning around at 7,200 RPMs, it's able to read the data fairly quickly, right? But if it's spinning around at 9,600 RPMs, then it's able to access that data even quicker. Now, like we still have, for the most part of computers, we still use hard drives, but a lot of times now you start seeing, what is it? Solid state drives now, which don't work on the same principle at all. It's not spinning, it's a direct access thing, and because of that, it ends up being quicker. It doesn't rely on this rate of spinning around. Still see that a lot, though. To have a solid state drive, it ends up costing you quite a bit more money to do that. All right, let's have a look at a couple questions to go with that at your desk, please. Questions 1 and 3 on page 250. Number 3 says a medical centrifuge is a device that separates blood into its parts. When you donate blood, how many people have donated blood? Nobody? Oh, okay, that's right, yeah, actually. Yeah, most of you guys are 16, right? That's right. When you turn 17, you can I don't think you have to be 18, actually. 17, yeah. When you donate blood, they take a pint of blood, which is about 500 milliliters of blood, and for the most part, they don't just transfuse that blood as it comes out of you into somebody else's body. They separate most blood into its components, and then they'll give people what component of blood that they need, like platelets or whatever of that blood that they need. So what they do to separate the blood is to put it into this thing called a centrifuge, which is basically a device that has a bunch of test tubes in it with the blood in it, and it spins around. And when it spins around, the heavier components of the blood end up separating. They go to the outside, and the lighter components don't go as much to the outside. Now, it's not as much in the news here right now, but it has been over the last few years. North Korea and Iran both have been nuclear concerns, and concern seems to be dying down a little bit in both cases. But one of the big things with North Korea and Iran is that, or one of the reasons that we knew that they were starting to develop nuclear programs years ago is that they were enriching uranium. Uranium is a mineral, a material that's found naturally, but most naturally occurring uranium isn't the right isotope or isn't the right type to be used in nuclear reactors and nuclear bombs. So you have to enrich it. You have to separate the uranium, the isotope of uranium that you want from the kind that you don't want. And the way that you separate it is with a centrifuge. You put it in the centrifuge and you spin it around, and then you end up getting the heavier uranium to the outside, and the lighter uranium doesn't go as much to the outside. So that's a centrifuge. Basically something that spins around. You may have been in a centrifuge yourself. Like if you go to the Stampede, they have this ride called the Gravitron, right? Which you get sucked to the outside. Yeah, at Callaway Park they have a ride like that, except you're not inside like you are in the Gravitron ride. Do you guys know what I'm talking about? Yeah, I can't remember what that one's called.
Is it that one that looks like a UFO in your strap?
Yeah. Yeah.
I hated that one.
That's essentially a centrifuge as well. If you were standing closer to the center, what you would find is that you would be pushed. I'll use that term loosely because we'll discuss in a couple of days why you're not actually pushed, but why you get the equivalent effect is being pushed to the outside. Like the heavier components of the blood, like the heavier isotope of uranium gets pushed to the outside. That's a centrifuge. All right, so this centrifuge can spin at 6.0 times 10 to the 4 RPMs. We want to know its frequency in hertz and its period. What is that number? 6.0 times 10 to the 4 RPMs. What does it represent? Yeah, it's 60,000, yes, but what does it represent in terms of its significance? Like what does it measure? It's frequency, yeah. Except it's not the frequency that we usually want. We want hertz. And of course, they're asking us for hertz there. So how do we get revolutions per second or hertz from this? Yeah, we're going to divide by 60. You're going to get less revolutions in 1 second than you get in a minute. Therefore, you must divide by 60 as opposed to multiply by 60. So let's figure that out now. 6.0 times 10 to the 4 divided by 60 is going to give me, I believe it's 1.00 times 10 to the 3. Is that right? Oh, yeah. The answer's right there in front of me. 1.0 times 10 to the 3 revolutions per second or hertz. There's my first answer. Now, what's the period of this? The time for one revolution. You can imagine if it makes 1,000 revolutions in a second, the time for one revolution is going to be very small. How are we going to find that out? The period is equal to 1 over the frequency. This is the equation that is on my data sheet, right? 1 over 1.0 times 10 to the 3. Now, you can say on your calculator 1 over that, or once again, you can just say 1,000. X to the minus 1 gives me 0.001. Or we could express it as 1.0 times 10 to the negative 3. And what would the units be? Hertz was revolutions per second, so the period here would be seconds. 1.0 times 10 to the negative 3 seconds. Does that make sense? These are pretty straightforward questions so far, right? I think you're going to find in this unit, there are some tricky questions for sure, but I think you're going to find that by and large, the questions end up being a little bit easier than some of them were in the last unit. Now, having said that, we still do some FNet stuff, but it just seems to be a little bit easier for the most part than it was in the last unit. Okay, let's try another one. And this one says a pebble stuck in the treads of a tire at a distance of 36 centimeters from the axle takes 0.4 seconds for the wheel to make one revolution. What's the speed of the pebble at any instant? I don't know if you guys have ever had anything like this. Probably not because of your age. Okay, when I was younger, and I wanted to know how fast I was going on my bike, like I would go out cycling a lot, and I would want to know how fast I was going and how far I had traveled, then I would use a little bicycle computer. You spend like 30, 40 bucks on a little bicycle computer, and it would give you your speed, it would give you your distance traveled, and so on. Now you just use GPS on your watch, right, or on your phone, so you don't need something like that anymore. But it hasn't been that long since we used something like a bike computer. Now, how did a bike computer work? Basically like this. You would put this little magnet, or this little, I shouldn't say this little magnet, this little conducting device, basically a coil of wire on a spoke of your bike. And that would be, the magnet would be on the spoke of the bike. The little conducting wire would be attached to the fork going down on either side of the wheel, right? You guys know what I'm talking about? Okay. So that conducting wire would be attached to a wire which would go to the bike computer. Now, every time, didn't matter where you put it on your wheel, didn't matter. Okay, every time it spun around, the magnet would go past that little coil of wire. And as the magnet went past that coil of wire, it would induce a small electric current every time it went past. So as it went around, okay, the little bike computer would count how many times it went by, and it would time it, how many times it went by per second. And then it would, from that, calculate the period, and then from that, it would calculate the speed. And it would do that all within a fraction of a second. But in order to do that, you had to program in to this little bike computer the radius of your tire, the radius of your wheel, your bike wheel. Because if you didn't program that in, there was no way of the bike computer calculating the speed. Remember, 2 pi r radius over the period. It measured the period itself, but you had to program in the radius of your tire in order to get an accurate result. Worked pretty well. Not as good as a GPS, but worked pretty well. This is essentially the same thing, except it's a pebble that just happens to be stuck in the tire as opposed to something that we're planning, right, with like a bike computer or whatever. All right, what's the speed of the pebble at any instant? What do we have here? R is 0.360 meters. We want to be in meters. Something is 0.40 seconds. What's that? The time that it takes to make one revolution. Is that the frequency or is that the period? What is it? It's the period, yeah. Big T. Don't make it little t, right? That's just general time. This is big T. And we want to find the speed. We're going to find the speed by using 2 pi r over t. And we have the value of r and we have the value of t. Hey, what if we had been given the frequency instead of the period here? We're given the period, which makes this pretty easy, right? 2 pi times 0.360 divided by 0.40. But what if we had been given the frequency instead? You could do that, right? You just calculate the period using 1 over f, and then you would sub it into this equation. So we're going to say 2 times pi times 0.360, 2 times pi times 0.360. We're going to divide that by 0.4. Gives us a value of 5.65 meters per second. So if this is not a rock on your tire, but rather it's a little magnet on a spoke that runs by every time your wheel turns around once, runs by a little wire that's attached to the fork of your bike, then or our bike computer has just calculated the speed of your bike, and it reads it digitally on the handlebars of your bike. Okay, from that, of course, it can calculate the distance that you travel based on the speed and the time that you travel. Does that make sense? Gotten a little bit harder, right? Certainly harder than those first 3 questions that we worked on, but not too bad. Still involving just a couple of equations that we learned here. Try these 2 questions, please, on page 251 now. So look at number 2. It says, in 2006, an Alberta astronomer discovered the fastest spinning collapsed star called a pulsar ever found. It has a radius of only 16.1 kilometers. Think about that. Okay, the star has a radius of 16.1 kilometers, which means its diameter, one side to the other, is basically the distance of here to 3/4 of the way to downtown Calgary. Well, no, it's a little further than that, but yeah, a little further than that. But downtown Calgary is about 40 kilometers from here, so we would say maybe about from here to Chinook Center. That seems like a long way sometimes when we're driving, but if you're talking about that as being the diameter of a star, that's pretty small. So we have this star, 16.1 kilometers in radius, and it's spinning at a rate of 716 hertz. This is the mind-boggling part. It's spinning 716 times around per second. Okay, we on Earth spin around how quickly? Once in 24 hours. This spins around 716 times in 1 second. So it's spinning pretty quick. We want to know the speed at the equator. So we're going to say for this one, R is 16.1 times 10 to the 3 meters. We're going to say that the frequency here is 716 hertz. And we're going to solve for the speed here. You can say V is equal to 2 pi r over t, because that's the equation that describes uniform circular motion. R has a value of, what, 16.1 kilometers? But we don't know what 16.1 times 10 to the 3 meters, but we don't know what t is, so we've got to find that. Any ideas? T is equal to 1 over the frequency. T is equal to 1 over f, so it's 1 over 716. What does that work out to be? 0.0 what? 0. Thank you. 0.00139 seconds. So it takes 1/1000th of a second for this thing to spin around once on its axis. Let's sub that in here now and see what we get. 2 times pi times 16.1 times 10 to the 3. Or, listen, you could just move the decimal place over 3 places. 16,100 would be fine. Divide it by the period, which is 0.00139 seconds. We do that math and it works out to be, I assume, the answer that's in your book, 7.24 times 10 to the 7 meters per second. Like, that's crazy fast. That's insanely fast. That's actually approaching the speed of light, which is the fastest that anything can possibly travel. Speed of light is 1 billion kilometers per hour. This isn't quite that fast, but it's close. There's a lot of reasons why you could not be on the surface of this star, this pulsar, but one of them is that if you were standing on the surface of it, what would happen to you as a result of the speed? It would throw you right off in a tiniest fraction of a second, right? Make sense?